What if the world around you, the chair you're sitting on, the screen in front of you, even the thoughts in your head aren't real, not in the way you've always believed? What if reality, as we know it, is just an elaborate illusion, a facade hiding something far stranger beneath? This isn't the plot of a sci-fi movie. It's a question that some of the brightest minds in physics, philosophy, and cosmology are seriously asking today. And the answers they've uncovered will make you question everything you thought you knew about existence itself. From the mind-bending realms of quantum physics, where particles defy logic by existing in multiple places at once, to the startling possibility that we might all be living inside an advanced computer simulation reality is far weirder than we've been taught. Think about it. Right now, scientists are debating whether the universe is a hologram, whether time is an illusion, or if countless parallel versions of you are making different choices in alternate dimensions. These aren't just wild guesses. They're theories backed by equations, experiments, and observations that challenge the very foundation of what we call real. So buckle up, because over the next 30 theories, we're going to peel back the layers of reality, one astonishing idea at a time. Some will sound like science fiction until you hear the evidence. Others will leave you staring at your hands, wondering if they're even yours. But one thing's for sure, by the end, you'll never look at the world the same way again. Are you ready to question everything? Let's begin. Imagine being the only real thing in existence, every person you've ever met, every place you've ever been, even the device you're holding right now, nothing more than illusions conjured by your own mind. This is the eerie foundation of solipsism, a philosophy so unsettling that even its critics struggle to disprove it. At its core, solipsism argues that the only certainty in existence is your own consciousness. Everything else, the physical world, other people, even the laws of physics, could just be elaborate constructs of your imagination. The seeds of this idea trace back centuries, but no one articulated it more famously than René Descartes, the 17th century philosopher who stripped away all assumptions in his search for absolute truth. His famous conclusion, "I think, therefore I am," became the bedrock of solipsistic thought. If doubting your own existence requires a thinker to do the doubting, then at the very least your own mind must be real. Everything beyond that, potentially a mirage. Modern versions of this idea take even wilder forms. Picture the brain in a vat thought experiment. What if your brain has been removed from your body, placed in a vat of nutrients, and hooked up to a supercomputer feeding you a perfectly simulated reality? Every sensation, memory, and interaction you've ever had could be artificial. There's no way to definitively prove this isn't the case after all. Any evidence you'd use to disprove it could itself be part of the simulation. What makes solipsism so chilling isn't just its logic, but its loneliness. If true, you'd be utterly alone, the sole conscious entity in an otherwise empty universe. Yet for all its bleakness, the theory holds a strange kind of power. It forces us to confront the limits of what we can truly know. Even science, for all its rigor, starts with the assumption that our senses and instruments report something real. Strip that away, and solipsism stands unchallenged, a ghost at the feast of human knowledge. Solipsism might seem like an unshakable philosophical fortress, but modern science is chipping away at its walls with some startling discoveries. Take neuroscience. Researchers can now peek inside your brain and reconstruct the images you're seeing just by analyzing neural activity. In one experiment, scientists used functional MRI scans to decode visual cortex signals, translating them back into rough versions of pictures participants were viewing. If your mind were truly the only reality, how could external machines intercept and interpret your private sensory experiences? This suggests at least some aspects of perception are grounded in measurable, shared physical processes rather than solitary mental constructs. Then there's the explosion of artificial intelligence systems that mimic human conversation so convincingly they pass the Turing test, fooling people into believing they're interacting with another conscious being. If consciousness can emerge from complex information processing, not just biological brains, the solipsistic stance grows even shakier. Why would your mind be the only real one when silicon-based entities exhibit similar behaviors? Of course, this leads us straight into David Chalmers' famous hard problem of consciousness, the mystery of why and how physical processes in the brain give rise to subjective experience at all. Even if we perfectly map neural correlates of consciousness, we still can't explain why red looks like red or why pain feels painful. Some researchers propose radical answers that flip solipsism on its head. Integrated information theory suggests consciousness isn't exclusive to humans, but exists everywhere information is processed, potentially even in simple devices like thermostats. Meanwhile, illusionists argue consciousness itself is a trick, a useful fiction our brains create. Both perspectives undermine solipsism's core premise by either distributing consciousness far beyond the self or dismissing it as a cognitive mirage. Yet for all these scientific advances, one nagging question remains: how can we ever truly prove that any experience exists outside our own? Every experiment, every measurement, every conversation filters through our private awareness. In the end, science may edge us closer to reality's nature, but the lone mind's prison walls still cast long shadows. What if our entire universe, with its galaxies, oceans, and coffee shops, is nothing more than an advanced simulation, lines of code written by some unfathomably intelligent civilization? This is the heart of simulation theory, a concept that's gained startling traction in recent years, championed by thinkers like philosopher Nick Bostrom and tech visionary Elon Musk. Bostrom's trilemma presents three stark possibilities, and at least one of them must be true. Either civilizations inevitably go extinct before reaching technological maturity, they lose interest in creating ancestor simulations, or we are almost certainly living in one right now. The logic is deceptively simple. If a civilization could one day run hyper-realistic simulations of its ancestors, and if they had even a modest desire to do so, the number of simulated minds would dwarf the number of biological ones. Statistically, the odds tilt heavily toward us being among the simulations. Musk puts it bluntly, there's a 1 in billions chance we're in base reality. He argues the rapid progression of video games, from Pong to photorealistic virtual worlds in just 50 years, hints at where technology could be in 1,000. If that trajectory holds, creating indistinguishable simulations would be child's play for a sufficiently advanced society. But the theory isn't without its critics. Physicists point out that simulating every particle in a universe would require unimaginable computing power unless shortcuts exist. Some suggest our universe's pixel-like limit, the Planck length, could be a telltale sign of rendering constraints like cosmic resolution. Others hunt for glitches, potential errors in the simulation, like anomalies in quantum behavior or mathematical constants that appear fine-tuned. Yet even if we found such glitches, could we ever prove they weren't just quirks of unsimulated physics? The deeper question simulation theory forces us to confront is one of purpose. If this is a simulation, why was it created? Are we someone's historical project, an ancestor's ethical experiment, or mere entertainment? And if we one day build our own simulations, would that make us creators, subjects, or both? The theory doesn't just challenge our grip on reality, it redefines what reality might even mean. Quantum physics might hold the first clues to whether we're living in a simulation or blowing the whole idea apart. At the subatomic level, particles behave in ways that defy common sense, existing in multiple states simultaneously until observed. This quantum indeterminacy has led some to speculate it could be evidence of optimization in a simulated universe. Just like a video game only renders the graphics you're looking at to save processing power, perhaps reality only loads the details when we measure them. The famous double-slit experiment, where particles act as both waves and particles depending on observation, could suggest the universe is conserving resources by not defining things until necessary. But there's a catch. Simulating quantum behavior at scale would require mind-bending computational resources, potentially more atoms than exist in the universe. This raises the simulation paradox. If creating a perfect simulation needs more energy and matter than the original reality contains, how could any civilization ever run it? Some theorists propose that future simulators might use mathematical shortcuts, approximating reality rather than replicating it perfectly. Others argue that quantum weirdness is simply how nature operates, with no need for simulation to explain it. Philosophers counter with an even sharper critique. If consciousness itself is required to render reality through observation, as some interpretations of quantum mechanics suggest, then the simulation would need to simulate consciousness first. This creates an infinite loop. The simulated minds would need their own simulated realities, requiring exponentially more power. The sheer scale quickly becomes nonsensical. Perhaps the most damning evidence against simulation theory comes from our own technology. As we build more complex simulations, from climate models to virtual worlds, we consistently hit computational walls. Even our most advanced supercomputers struggle to simulate a single human brain's neural activity in real time, let alone an entire universe. If we, the supposed creators of future simulations, can't overcome these limits, why assume some other civilization could? Yet the debate refuses to die because of one haunting possibility. What if the very laws of physics we're measuring are just the rules programmed into the simulation? Any attempt to find flaws might be doomed from the start, like a character in a video game trying to prove the game engine isn't real using the game's own logic. This leaves us circling back to the unsettling core of the argument. The harder we look for proof, the more the universe seems designed to keep us guessing. What if the physical world, the trees, the stars, even your own body, doesn't actually exist as solid, independent matter? This radical idea isn't from some modern sci-fi novel. It's the core of idealism, a philosophy championed by 18th-century thinker George Berkeley, who argued that reality is fundamentally mental. His famous dictum, "To be is to be perceived," flips our common-sense view of the world upside down. In Berkeley's universe, objects only exist when they're being observed or perceived by a mind. Close your eyes, and the room you're in wouldn't vanish into nothingness because God, the ultimate perceiver, is always watching. This might sound like philosophical whimsy, but fast forward 3 centuries and quantum mechanics starts whispering something eerily similar. Take the observer effect, where particles like electrons don't settle into definite states until measured. Before observation, they exist in a haze of probabilities, as if reality itself is waiting for a mind to collapse it into being. Some interpretations of quantum theory even suggest consciousness plays an active role in shaping the physical world. It's as if Berkeley's immaterialism got a scientific makeover, trading divine perception for quantum observers. Critics dismiss this as coincidence, pointing out that quantum observation doesn't require human consciousness. A camera or detector can trigger the same collapse. But idealists counter with a deeper question. What if all measurement devices are themselves mental constructs? After all, we only know about detectors because we perceive their outputs. The loop keeps tightening. Even more striking are experiments like the quantum delayed choice, where decisions made in the present seem to rewrite the past behavior of particles. It's as if reality is a canvas that only solidifies when we look at exactly the kind of behavior Berkeley might have predicted. Yet idealism faces its own paradoxes. If reality is purely mental, why does it feel so stubbornly consistent? drop a rock on your foot, and the pain isn't any less real because it's all in your mind. Berkeley's answer, that God maintains a shared, orderly experience, might not satisfy modern skeptics, but the theory's real power lies in its challenge to materialism. By suggesting that matter is secondary to perception, idealism forces us to ask what's truly fundamental, the atoms we can't see or the experiences we can't deny. In a world where virtual realities and AI consciousness blur the lines between mind and matter, Berkeley's 300-year-old ideas suddenly feel uncomfortably relevant. Kant's transcendental idealism takes Berkeley's mental universe and adds a crucial twist. What we perceive isn't just shaped by our minds, but by the very structures of human cognition itself. Imagine putting on a pair of glasses you can never remove, tinted with the colors of space, time, and causality. According to Kant, these aren't features of the external world, but the lenses through which we necessarily experience it. He called the raw, unfiltered reality, noumena, the world as it truly exists, independent of perception. What we actually engage with, though, is phenomena, reality as our minds reconstruct it, like a live-action filter applied to existence. Consider color blindness. Two people can look at the same apple. One sees vibrant red, the other murky green, yet both are convinced their perception is accurate. Kant would argue neither is seeing the apple's true, noumenal state. The fruit's real color might be something beyond human visual processing altogether, like a shade our brains can't even conceptualize. Our senses don't reveal reality, they translate it into terms we can understand, like a radio tuning cosmic static into music. This isn't just about vision. Time itself might be another one of those inescapable lenses. We experience events in a linear sequence, past, present, future, but what if noumenal reality has no timeline at all? Physics hints at this possibility. In Einstein's block universe, all moments exist simultaneously. Our brains, wired for cause and effect, slice this frozen block into a flowing narrative, like a film reel forced frame by frame through a projector. Kant's real genius was recognizing these structures as universal. Unlike Berkeley's God-dependent idealism or Solipsism's lonely mind, transcendental idealism suggests all humans share the same cognitive operating system. That's why we can agree on the color of stop signs or the order of historical events, not because we're accessing objective truth, but because we're all running the same mental software. The unsettling implication, even science for all its rigor, might just be the study of phenomena nature as filtered through human perception, not nature as it truly is. Critics pounce on this. If noumena are forever beyond our grasp, how can we even know they exist? Kant's answer walks a razor's edge. The very fact that our perceptions feel imposed upon us, that the world resists our whims, suggests some external source. But here's the twist that keeps philosophers awake. What if the external is itself a concept bound by our mental framework? The ultimate reality might not just be unknowable, it could be unthinkable, beyond the very categories of inside and outside our minds have built. Modern neuroscience lends eerie support. Brain scans show that what we call seeing is actually a cascade of electrical signals reconstructed into images. Patients with blind sight, damaged visual cortices who deny seeing anything can still navigate obstacle courses, proving perception and awareness aren't the same. It's as if their minds receive noumenal data but lack the phenomenological interface to render it consciously. Kant's theory ultimately does something remarkable. It splits the difference between solipsism and materialism. The world isn't purely mental or purely physical, it's an interaction, a negotiation between whatever's out there and the unchosen rules of human cognition. Like prisoners in a cave watching shadows, we might never see the fire casting them, but unlike Plato's cave, there's no exit. The walls are made of our own mind. Picture this: every event, every particle, every moment in our three-dimensional universe isn't happening where we think it is. Instead, it's all playing out on a distant, two-dimensional surface, like a cosmic movie projected onto the fabric of reality itself. This isn't fantasy, it's the holographic principle, a theory so profound it rewrites our understanding of space, time, and information. The idea first emerged from an unlikely place, the study of black holes. When physicists like Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of hidden information, they stumbled onto a paradox. How could a region of space that sucks in everything, even light, still preserve the information of what it swallowed? Enter Leonard Susskind. In the 1990s, he proposed a radical solution. The information isn't lost inside the black hole. It's encoded on its boundary, the event horizon, the point of no return. Think of it like a prison tattoo, but instead of ink on skin, it's quantum data etched onto the surface of the black hole. This led to an even wilder realization. If a black hole's interior can be described entirely by information on its edge, maybe the entire universe works the same way. Our 3D reality might just be a holographic projection from a 2D surface at the edge of the cosmos. To grasp this, imagine a credit card hologram. Tilt it, and a flat sticker suddenly appears three-dimensional. Now scale that up to universal proportions. The holographic principle suggests that everything we experience, the taste of coffee, the glow of stars, the sensation of wind, is just a vast, dynamic hologram generated from a hidden 2D layer. Even you, right now, might be a kind of information avatar, your entire existence derived from data written on the universe's outermost shell. But how could this possibly work? The math points to something called ad/CFT duality, a concept from string theory where a higher dimensional space, like our 3D world, precisely corresponds to a lower dimensional theory, a 2D boundary. It's as if the universe has a secret instruction manual written in a simpler language, and the 3D world we see is just the elaborate output. Critics argue this remains theoretical. After all, we can't exactly peek beyond the cosmic horizon to check. Yet tantalizing clues exist. Some physicists speculate that the universe's pixelation, the Planck length, the smallest possible unit of space, might be evidence of this underlying code, like seeing the individual dots in a newspaper photo under a magnifying glass. The implications are staggering. If true, the holographic principle would mean that space itself is an illusion, a kind of user interface for something far more fundamental. It also solves the black hole information paradox by ensuring no data is ever truly destroyed, just rearranged on a surface we can't see. Even time might emerge from this holographic dance, a secondary effect of deeper interactions. Yet for all its elegance, the theory leaves us with haunting questions. If we're holograms, who or what is the projector? Is the universe's boundary physical, or is it a mathematical abstraction beyond human comprehension? And most unsettling of all, if reality is a hologram, what happens when the cosmic battery runs out? The holographic principle doesn't just challenge our place in the cosmos, it redefines what place even means. You open the box, Schrödinger's cat lies motionless, no longer in that eerie quantum limbo between life and death. But here's the twist: in another universe, the cat is alive and well, purring as if nothing happened. Now replace the cat with you. This is the spine-chilling premise of quantum immortality, a theory where consciousness refuses to die, not through magic, but through the sheer mathematics of the multiverse. At its core, quantum immortality stems from the many-worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett in the 1950s. Unlike the Copenhagen interpretation where particles choose a state upon observation, Everett argued every possible outcome happens, just in separate, branching universes. Flip a coin and the universe splits, heads in one reality, tails in another. Now apply this to life and death. If countless versions of you exist across infinite timelines, there's always a universe where you survive, even against impossible odds. Imagine Russian roulette with a million-chambered revolver. Statistically, most versions of you die, but one version always pulls the trigger on an empty chamber. From that version's perspective, it feels like luck. From the multiverse's perspective, it's inevitable. Proponents argue your consciousness isn't special. It's just the one that keeps landing in timelines where you persist. The other versions, they're just as real, but their experiences stop the moment yours continues. Critics pounce on the theory's solipsistic flavor. If only the surviving versions of you remain conscious, doesn't that imply a bizarre form of selection bias? And what about aging? Even if you dodge every bullet, car crash, and illness, your body would eventually succumb to time, unless consciousness somehow jumps to younger versions in alternate realities. Some theorists take this further, suggesting quantum immortality might explain near-death experiences or glitches where people recall dying in dreams only to wake up unharmed. The darkest implication, you could be the only person who's truly immortal in your subjective experience. Everyone else might appear to die around you, but their consciousness branches into realities where they persist. It's a lonely paradox, a cosmos where no one ever subjectively experiences their own death, yet mourns others' endings. Quantum immortality doesn't just challenge our fear of death, it warps our understanding of identity. Are you a single thread of awareness or a fractal of possibilities? And if every choice spawns new universes, does free will exist? Or are we just passengers riding the branching paths of probability? The theory offers no comfort, only a dizzying vision of existence where death is both inevitable and impossible, depending on where, or rather when, you look. Time doesn't flow, it just is. That's the jarring claim of eternalism, the idea that past, present, and future exist simultaneously in a vast, unchanging four-dimensional block. Imagine the universe as a cosmic DVD, where every moment from the Big Bang to the heat death of everything is already recorded. What we call now is just the scene your consciousness happens to be playing. Einstein laid the groundwork for this when his theory of relativity shattered Newton's clockwork universe. If you've ever heard that time is the fourth dimension, this is what it means. Relativity shows that time isn't universal, it stretches and warps depending on speed and gravity. Two events happening at the same time, for you might occur years apart for someone near a black hole. This makes now slippery, more like a personal perspective than an objective fact. Enter light cones, the tool physicists use to map causality in spacetime. Picture throwing a pebble into a pond. The ripples expand in circles at a fixed speed. In space-time, every event creates a similar ripple. A future light cone events it can affect, and a past light cone events that could affect it. But here's the catch. Outside those cones lie events so distant that not even light could connect them to you. They're neither past nor future, just elsewhere, frozen outside your timeline like a paused movie reel. This reshapes how we view reality. Your birth isn't gone, it's still out there in the block, just as real as this moment. The same goes for events you think haven't happened yet. In the block universe, the distinction between past and future is an illusion, a quirk of human perception, like fish believing water is the only possible environment. Philosophers call this the moving spotlight theory. Consciousness glides along the timeline, mistaking its current position for all that exists, but physics suggests otherwise. When we observe distant galaxies, we're literally looking into the past because their light took millennia to reach us. Meanwhile, aliens in those galaxies might be observing Earth right now and seeing dinosaurs. Which moment is truly present? The block universe's answer, all of them. Critics argue eternalism drains life of meaning. If the future's already written, why strive for anything? But proponents counter that free will isn't about creating outcomes. It's about experiencing the path your choices carve through the block. Think of it like a novel. The ending exists the moment you start reading, but the journey still thrills. The eeriest implication: if the block is static, then death is just a location in spacetime, not an end, but a fixed point your consciousness hasn't reached yet. You're always alive somewhere in the mosaic. This doesn't comfort those grieving lost loved ones, but it hints at a universe far stranger than our linear instincts suggest, one where every moment from your first breath to your last persists forever in the grand architecture of existence. What if consciousness isn't something special that emerges from complex brains, but instead a basic feature of the universe itself, as fundamental as space, time, or matter? This is the bold claim of panpsychism, a theory that turns our understanding of the mind inside out. Instead of asking how neurons create awareness, panpsychists ask, what if awareness was here first, woven into the fabric of reality at every scale? Picture a universe where even an electron has some tiny spark of experience, not thoughts or feelings as we know them, but a raw, primitive form of consciousness. This idea isn't new. Ancient philosophies from Buddhism to indigenous cosmologies have long suggested that mind and matter aren't separate. But today, panpsychism is getting fresh traction through integrated information theory, or EIT, developed by neuroscientist Giulio Tononi. IIT proposes that consciousness isn't about what a system is like a brain, but about how its parts interact. The more interconnected and complex those interactions, the richer the conscious experience. Under this framework, even a humble thermostat might possess a sliver of awareness, not because it thinks, but because it processes information in a way that meets IIT's mathematical criteria for consciousness. Critics like Daniel Dennett pounce on this as absurd. If everything's conscious, they argue, the term loses all meaning. Dennett's illusionism counters that consciousness itself is a trick, a user interface our brains generate to simplify reality. To him, panpsychism commits the fallacy of misplaced concreteness, mistaking abstract patterns for real inner experience. But panpsychists fire back. Why would evolution produce a vivid, continuous stream of awareness if it were just decorative? Pain feels like pain, not a handy metaphor. The debate gets even stranger when quantum physics enters the picture. Some interpretations suggest particles exhibit proto-conscious properties like the way they choose states during observation. Nobel laureate Roger Penrose and anesthesiologist Stuart Hameroff proposed that microtubules in brain cells harness these quantum effects to generate consciousness. If true, it hints that the boundary between mind and matter might blur at the smallest scales. Yet panpsychism's real power lies in solving the hard problem of consciousness, why subjective experience exists at all. Traditional materialism struggles to explain how neurons firing create the taste of chocolate or the sting of regret. Panpsychism flips the script. If experience is fundamental, then brains don't produce consciousness, they channel it, filtering and amplifying a property already present in the cosmos. The implications are staggering. If consciousness is universal, ethical questions explode. Should we consider the experiences of AI, ecosystems, or even particles? And if reality is inherently experiential, does that mean the universe itself has some form of mind? Panpsychism doesn't just reshape our place in the cosmos, it suggests the cosmos might be more alive than we ever imagined. Here's a mind-bending possibility. What if you're not a product of billions of years of evolution, but a fleeting accident? A disembodied brain that spontaneously formed from random quantum fluctuations, complete with false memories of an entire life. Meet the Boltzmann brain, one of the most unsettling thought experiments in cosmology. Named after 19th century physicist Ludwig Boltzmann, who linked entropy to the arrow of time, the idea emerges from a simple question. In an infinite universe governed by probability, could randomness conjure a self-aware entity out of pure chaos? Boltzmann's work revealed something startling about entropy, the measure of disorder in a system. While entropy generally increases over time, why coffee cools and eggs don't unscramble, tiny decreases can still occur through statistical flukes. In a vast enough cosmos, given enough time, even the most improbable events become inevitable. That includes the spontaneous assembly of particles into a fully formed, conscious brain. The math suggests it's far more likely for a lone, self-aware fluctuation to pop into existence than for an entire ordered universe like ours to arise naturally. This leads to a paradox so sharp it keeps cosmologists up at night. If Boltzmann brains are statistically favored, why do we find ourselves in a coherent 13.8 billion-year-old universe instead of as momentary aberrations? Some theorists argue this very observation disproves the idea. If we were Boltzmann brains, our memories and perceptions would be untrustworthy fragments, not the consistent reality we experience. Others counter that a real universe could still produce Boltzmann brains, meaning you can't rule out being one. It's like a hall of mirrors where every reflection doubts its own existence. The debate intensifies when quantum field theory enters the picture. In a vacuum, particles constantly blink in and out of existence, a phenomenon called quantum foam. Given infinite time, could these fluctuations assemble something as complex as a functioning mind? Critics point out that even if possible, such brains would last nanoseconds before dissolving back into chaos. But proponents highlight an eerie loophole. If a Boltzmann brain forms with the false memory of stability, its subjective experience might feel continuous even as it winks out of existence. The theory's real sting lies in its implications for science itself. If consciousness can emerge from random noise, our entire framework for testing reality, from fossil records to cosmic microwave background, might be illusions concocted by a transient fluctuation. It's solipsism dialed up to cosmic scales, where even the laws of physics become suspect. Some physicists sidestep this by invoking the anthropic principle. Universes that don't produce stable observers like ours simply go unobserved. Others suggest the multiverse could dilute Boltzmann brain probabilities, making ordered realities like ours more common. Yet the Boltzmann brain isn't just a philosophical quirk, it's a stress test for our models of reality. If our best theories predict phenomena that undermine their own validity, do we need new physics? Or does the mere fact we're debating this prove we're not Boltzmann brains after all? The theory leaves us stranded between two terrifying possibilities, that we're impossibly rare or that we don't exist at all. Either way, it forces us to confront the fragility of everything we call real. Long before quantum physicists grappled with virtual particles popping in and out of existence, ancient Hindu sages spoke of reality itself as a grand illusion, a cosmic dance of appearances called Maya. In the Vedas, texts dating back over 3,000 years, the material world isn't dismissed as fake, but revealed as something subtler, a temporary, ever-shifting projection of a deeper, unified reality. Picture a magician's rope trick where a coiled rope appears as a swaying serpent to the audience. The rope is real, but the serpent is Maya, not quite false, yet not ultimately true. This idea finds eerie resonance in modern physics. Quantum field theory shows us that empty space isn't empty at all. It's a seething foam of virtual particles that flicker into being only to vanish moments later. These particles aren't illusions in the sense of being fake. They're measurable effects with real consequences, like the Casimir force pushing metal plates together in a vacuum. Yet they lack the permanence we associate with real objects. In this light, Maya isn't about deception. It's about the dynamic, impermanent nature of existence, where even solid matter is mostly empty space held together by fleeting interactions. The Upanishads, Hinduism's philosophical core, take this further. They describe Brahman, the ultimate reality, as formless, infinite, and beyond human perception, while Maya is the creative force that spins diversity from this unity, like sunlight refracting into colors through a prism. Here's where it gets mind-bending. Modern cosmology's holographic principle echoes this framework. If our three-dimensional universe is a projection from a two-dimensional boundary, as some physicists propose, then Maya becomes a metaphor for the cosmic rendering of reality from a simpler, hidden substrate. But Maya isn't just physics, it's psychology. Hindu philosophy warns that human suffering stems from mistaking the illusion for the real. We chase wealth, status, and permanence in a world designed to change, like building sandcastles against the tide. Quantum mechanics unintentionally mirrors this insight. Particles behave differently when observed, suggesting reality responds to perception. Is Maya the universe's way of reflecting back our own expectations and attachments? Critics argue Maya discourages engagement with the material world. Yet Hindu teachings clarify that the goal isn't rejection but recognition, to interact with life's dance without clinging to its forms. Compare this to physicists who study virtual particles. They don't deny their existence but understand their transient nature. The parallel is uncanny, an ancient spiritual concept and cutting-edge science both pointing to the same unsettling truth. Reality is far more fluid and far less solid than our senses insist. The most profound implication: if Maya is real, then enlightenment, seeing through the illusion, might not be about transcending reality but perceiving it more clearly. Just as quantum physicists use equations to glimpse the invisible underpinnings of matter, the sages used meditation to pierce Maya's veil. Both paths, separated by millennia, lead to the same startling conclusion. What we call real might just be the tip of an unimaginable iceberg. What if the universe isn't just described by mathematics, but is mathematics? This radical idea comes from cosmologist Max Tegmark, who argues that reality isn't merely governed by numbers and equations, it is numbers and equations. Imagine peeling back the layers of existence until you're left with nothing but pure mathematical structure. No particles, no forces, just abstract relationships humming in the void. Tegmark calls this the mathematical universe hypothesis, and it suggests that everything you experience, the warmth of sunlight, the taste of coffee, even your own thoughts, are all just intricate patterns in an eternal, unchanging mathematical tapestry. The foundation of this idea rests on what physicist Eugene Wigner famously called the unreasonable effectiveness of mathematics. Why do equations penned by humans, creatures who evolved to dodge predators and gather berries, capture the behavior of black holes, quantum particles, and galaxies with such eerie precision? From Newton's laws to Einstein's relativity, math predicts phenomena we haven't even observed yet, like gravitational waves or the Higgs boson. Tegmark's answer is simple: math works because reality is math. The universe isn't running on mathematical rules like a computer obeying code. It's the rules themselves playing out in every possible configuration. This leads to Tegmark's most mind-stretching prediction, the Level 4 multiverse. While most multiverse theories imagine parallel worlds with different physics like bubble universes or branching quantum timelines, Tegmark's Level 4 goes further. It proposes that every mathematically coherent structure exists as a physical reality somewhere. Not just slight tweaks to our universe's constants, but entirely alien realities governed by geometries and equations we can't even fathom. Picture a cosmos where time flows backward in fractal spirals, or where gravity behaves like poetry, pulling objects together in rhyming pairs. If it can be described mathematically, it exists somewhere in the sprawling multiverse. Critics argue this is more metaphysics than physics. How could we ever test the existence of universes based on equations we've never written? Tegmark counters with a thought experiment. Imagine a fish scientist in a pond. No matter how brilliant, it could never derive the laws of quantum field theory. Its reality is too limited. Similarly, our brains might be evolutionarily unequipped to perceive or describe the full spectrum of mathematical realities. The fact that we've uncovered as much math as we have might just be a lucky accident, like a toddler stumbling upon a single correct note in a symphony. Yet Tegmark's theory holds a strange comfort. If true, it means the universe isn't arbitrary or whimsical, but fundamentally knowable, not because we're special, but because math is all there is to know. Even consciousness under this framework might reduce to a particular kind of information processing, a dance of algorithms that feels like something from the inside. The mathematical universe doesn't just redefine reality, it erases the line between the physicist's chalkboard and the stars. Close your eyes and touch your nose. How do you know it's really there? Not because of textbooks or physics, but because of the raw, immediate experience of feeling it under your fingertips. This is the heart of phenomenology, a philosophy forged by Edmund Husserl in the early 20th century that flips reality on its head. Forget atoms, equations, or even the external world. Husserl argued that the only thing we can truly be certain of is our own lived experience. Everything else, the chair you're sitting on, the screen in front of you, even the laws of science, are just interpretations piled atop that primal foundation. Take something as simple as an optical illusion. Stare at the famous checker shadow illusion, where two squares labeled A and B appear radically different shades until you connect them with a finger, revealing they're identical. Your brain didn't lie, it interpreted. Husserl would say this isn't a bug of perception but a feature of consciousness itself. Reality isn't given to us neutrally, it's constructed through layers of interpretation, like a painter adding brushstrokes to a canvas. Even time, in Husserl's view, isn't a fixed river but a flowing tapestry woven by memory, anticipation, and the ever-fleeting now. Husserl's method, called epoché, pushes this further. Imagine mentally bracketing all your assumptions that the sky is blue, that gravity exists, that other people have minds, and focusing solely on how these things appear to you. Not whether they're real, but the raw experience of blueness, heaviness, or emotion. It's like stripping away the labels on a map to feel the terrain beneath. Modern neuroscience accidentally confirms this. When you see a red apple, your brain doesn't process redness as an objective property. It combines wavelengths, memory, and context into a seamless experience, one that could differ wildly for someone else without either of you realizing it. Critics dismiss phenomenology as navel-gazing. If everything's filtered through consciousness, how can we trust any shared reality? But Husserl's legacy thrives in fields from artificial intelligence to virtual reality design. When engineers build immersive VR, they're not replicating physics. They're hacking perception, manipulating Husserl's life world to fool your senses. Even the hard problem of consciousness leans on his ideas. If experience is the one undeniable fact of existence, maybe it's the ground zero we should study first. The theory's real power lies in its humility. While physics chases grand unified theories and metaphysics debates the nature of being, phenomenology starts with a simple truth. Before we theorize about reality, we should understand how it feels. Because in the end, whether the universe is a simulation, a hologram, or a mathematical structure, the only thing you'll ever truly have is the next moment of experience, ripe, immediate, and utterly undeniable. What if reality isn't just something we observe, but something we actively create by the very act of looking? This is the startling claim of the participatory anthropic principle, a theory that places consciousness at the heart of cosmic existence. It all started with physicist John Wheeler, who took quantum mechanics observer effect and stretched it to cosmic scales. In his famous delayed choice experiment, Wheeler showed that a particle's past behavior, whether it acted as a wave or a particle, could be altered after the fact depending on how the experimenter chose to measure it. It's as if the universe waits for us to make up its mind, retroactively rewriting its own history based on our decisions. Wheeler took this further with his it-from-bit hypothesis, suggesting that the physical universe, it, might emerge from information, bit, with conscious observers as the ultimate source. Imagine a cosmic game of 20 questions where the universe only solidifies its answers when someone asks the questions. This radical view implies that without observers, reality remains a fog of possibilities, no stars, no planets, just quantum potential waiting to be collapsed into actuality. But what does this mean for us? Enter biocentrism, a controversial theory proposed by scientist Robert Lanza. Lanza argues that life and consciousness aren't accidental byproducts of the universe, they're its fundamental purpose. In a biocentric cosmos, space and time aren't rigid containers but tools our minds use to organize experience. Think of it like virtual reality goggles. The software generates a 3D world only when you put them on. Similarly, Lanza suggests the universe might require observers to render its reality. Critics dismiss this as idealism in a lab coat. They point out that the delayed choice experiment doesn't need consciousness. A photon hitting a detector can trigger the collapse just as well as a human eye. Philosophers like Daniel Dennett go further, accusing biocentrism of conflating perception with creation. After all, trees fell in forests long before ears evolved to hear them. Does that mean the sound didn't exist? Yet the theory gains eerie traction when applied to cosmology's fine-tuning problem. The universe's constants are so precisely calibrated for life that even slight changes would make galaxies, chemistry, or even atoms impossible. Biocentrism offers a provocative explanation. Maybe the universe had to be this way because conscious observers eventually emerged to see it. It's not that the universe was designed for us, but that our existence defines it, like a mirror that only reflects when someone looks. The debate reaches its peak with the quantum suicide thought experiment. Imagine a device that measures a particle's spin. If it's up, the device kills you. If down, it spares you. Quantum mechanics says the particle exists in both states until observed. Biocentrism suggests your consciousness would always find itself in the timeline where you survive, because the alternative branches have no observer to experience them. It's a macabre twist on Schrödinger's cat, where the act of observation doesn't just determine reality, it determines whose reality gets to exist at all. Whether you find this empowering or unsettling, the participatory anthropic principle forces a profound question. Are we passive spectators in a pre-written universe or co-authors of a story still being told? The answer might lie somewhere in between, not a universe that requires observers, but one that becomes richer, more complex, and perhaps even more real because we're here to see it. Everett's many-worlds interpretation doesn't just suggest alternate realities might exist, it insists they must. Picture Schrödinger's cat not as a morbid puzzle, but as a cosmic fork in the road. The moment the box opens, the universe doesn't choose between life or death. It splits into two equally real branches, one with a purring feline, the other with a still corpse. Unlike the Copenhagen interpretation, where observation collapses quantum possibilities into a single outcome, Everett's math shows these possibilities never actually resolve. They simply diverge like parallel train tracks multiplying endlessly into the future. Here's where it gets wild. Every quantum decision, every electron spin, every photon's path spawns new universes. That coffee you debated drinking this morning, in one world you took a sip, in another you left it untouched. The mind-bending implication: there's a version of you who became an astronaut, another who moved to Bali, and countless others making choices you'd never dream of. This isn't science fiction, it's the unflinching consequence of quantum mechanics when you remove the observer as a special player. But how does this branching actually work? Enter quantum decoherence, the process that makes parallel worlds invisible to each other. Imagine tossing a pebble into a pond, ripples spread outward, interfering with each other. Now picture two pebbles dropped at once. At first, their ripples overlap, creating a complex pattern, but over time they separate, becoming distinct. In quantum terms, this is what happens when a system interacts with its environment. The ripples of different states stop overlapping and become isolated realities. That's why you don't see ghostly echoes of alternate selves. Decoherence ensures each timeline unfolds independently, like radio stations playing different songs on the same frequency. Critics pounce on the theory's extravagance. If every quantum event spawns universes, wouldn't that require unfathomable energy? Everettians counter with a cosmic twist. The multiverse doesn't create new energy, it redistributes existing possibilities. Think of it like shuffling a deck of cards. Every possible hand already exists in the permutations. You're just seeing one deal. Similarly, all outcomes mathematically exist in the universal wave function. We simply experience one thread. The most haunting question isn't whether these worlds exist, but what it means for you. If every choice branches reality, does free will vanish? Not necessarily. Your decisions still matter. They determine which branch this version of you experiences. It's like a choose-your-own-adventure book where every page turn spawns new copies of the story, each equally valid. And here's the kicker: many worlds might solve time's arrow. In a block universe where past and future equally exist, why do we remember yesterday but not tomorrow? Decoherence could explain it. Branches only flow forward because reverse paths cancel out quantum interference, making the future feel open while the past stays fixed. The theory's real power lies in its simplicity. No hidden variables, no mysterious collapses, just pure quantum evolution unfurling into infinity. Whether you find it liberating or terrifying, one thing's clear: if ever it was right, reality isn't just stranger than we imagine. It's stranger than we can imagine, with every possibility playing out somewhere in the cosmic kaleidoscope. Most theories about reality push the boundaries of science, but some bulldoze right through them, leaving logic in the dust. Enter Time Cube, the bizarre brainchild of self-proclaimed genius Jean Ray, who claimed to have discovered that Earth experiences not one but 4 simultaneous days at once. Forget linear time. This theory insisted that every 24-hour period we experience is actually 4 distinct days overlapping, with the sun simultaneously shining on opposite sides of the planet. Morning, noon, evening, and midnight weren't phases of a single day, but separate coexisting realities stacked like layers in a cosmic lasagna. Ray's evidence: a mix of disjointed word salad and crude diagrams showing Earth split into quadrants, each living its own day independent of the others. He argued that humanity's failure to recognize this proved we were trapped in educated insanity, brainwashed by academic gatekeepers who suppressed his revolutionary truth. The theory's peak absurdity came with Ray's declaration that he'd achieved singularity, becoming the only human to perceive all 4 days at once, a claim he illustrated by photos of himself posing with makeshift Time Cube props at roadside diners. What makes Time Cube fascinating isn't its validity. There isn't any, but its cultural afterlife as a meme before memes existed. It became a magnet for internet ridicule, yet also a bizarre symbol of anti-establishment defiance. Ray railed against everyone from NASA to kindergarten teachers, casting himself as a lone truth teller in a world of sheep. In that sense, Time Cube taps into a deeper tension: humanity's love-hate relationship with reality rebels. We mock them mercilessly: flat earthers, hollow earthers, those convinced the moon is a hologram, yet secretly, part of us thrills at the idea of someone smashing the rules. Science thrives on dissent, but there's a chasm between challenging paradigms and detonating them with clownish bravado. Compare Ray to Einstein, who overturned Newtonian physics with math and evidence, not rants about quadrant days. Still, Time Cube forces a question: how thin is the line between genius and gibberish? Most outliers are wrong, but history shows a few, like Wegener with continental drift, were laughed at before being vindicated. The difference: predictable patterns. Wegener's theory explained real data. Ray's crumbled under basic scrutiny, like claiming time zones disprove linear time when they actually confirm it. The theory's legacy is a funhouse mirror reflecting our era's crisis of trust in expertise. When institutions falter, conspiracy theories flourish, and reality becomes a choose-your-own adventure. Time Cube's absurdity is obvious, but its endurance as a cult curiosity reveals something unsettling. In a post-truth world, the loudest voice often drowns out the most reasoned one. Maybe that's the real fourth dimension Ray uncovered, not a secret structure of time, but the warped space where reason and nonsense now collide. What if every star, every atom, every law of physics is just information being processed by some cosmic computer? This is the core of digital physics, the radical idea that the universe isn't just described by math, but fundamentally runs on it like an unfathomably complex simulation. Forget particles and waves. At the deepest level, reality might be nothing more than bits flipping in an endless, invisible calculation. Stephen Wolfram, the mind behind computational irreducibility, pushes this even further with cellular automata, simple grids where basic rules give rise to staggering complexity. His famous Rule 110, a one-dimensional automaton with just a handful of instructions, generates patterns so intricate they resemble organic structures, galaxies, even cryptography. If such complexity emerges from simple rules, Wolfram argues, why couldn't our universe be the output of a cosmic algorithm? It's not that some programmer wrote the code, it's that computation might be nature's native language with physics as its output. Then there's the Church-Turing thesis, a cornerstone of computer science stating that any computable problem can be solved by a Turing machine. Apply this to cosmology and you get a provocative question. If the universe's behavior can be calculated, even in principle, does that mean it is a computation? Some digital physicists take this as gospel, suggesting spacetime is a lattice of discrete points processing information, like a quantum Minecraft grid. Even gravity and quantum mechanics might just be emergent properties of this underlying computation, the way fluid dynamics emerge from countless molecular interactions. But where's the proof? Glitch hunters point to cosmic anomalies as potential bugs in the system. Take the Mandela effect, where swaths of people misremember details like the Berenstain Bear's name or the Monopoly Man's monocle. Could these be patches in reality's source code? More concretely, physicists have debated whether the universe's pixelated limit, the Planck length, hints at a computational substrate, like the resolution of a digital display. Others cite quantum indeterminacy as potential evidence of processing limits, where the cosmos renders outcomes only when observed to save resources. Critics fire back with thermodynamics. If the universe were digital, wouldn't computations generate detectable heat? Yet proponents counter with black hole entropy, the idea that information isn't lost but encoded on event horizons, exactly as you'd expect from a self-correcting cosmic hard drive. The debate rages because digital physics straddles philosophy and hard science, offering answers that are as elegant as they are untestable. The theory's real allure is its democratization of reality. If existence is computational, then the difference between a star and a smartphone is just scale. Both are information in motion. It's a vision both humbling and liberating, where the cosmos isn't a machine but an equation solving itself, one Planck length tick at a time. What if nearly 300 years of human history never actually happened, not because they were forgotten, but because they were deliberately invented? This is the jaw-dropping claim of the phantom time hypothesis, proposed by German historian Herbert Illig in the 1990s. According to Illig, the years 614 to 911 were entirely fabricated by a conspiracy involving the Holy Roman Emperor Otto III, Pope Sylvester II, and possibly even Byzantine rulers. Their motive: to place themselves at the symbolic center of history by aligning the calendar with significant dates like the supposed millennium of Christ's birth. The theory hinges on discrepancies in historical records, architectural styles, and astronomical observations. Illig noticed that the Gregorian calendar, introduced in the 1500s to correct drift in the Julian calendar, required a 10-day adjustment. But based on his calculations, the error should have been 13 days if those phantom centuries were real. Even more striking, our dendrochronology reports tree ring data from ancient European oaks that show gaps in the expected growth sequences around the disputed period. To Illig, this wasn't just missing data, it was proof those trees never lived through those years at all. But could an entire chunk of history really be forged? The logistics boggle the mind. Fabricating 3 centuries would require rewriting countless documents, altering genealogies, and convincing generations of scholars across continents to play along. Illig's detractors point out that while medieval chronology has inconsistencies, other civilizations' records like the Tang dynasty in China or the Islamic Golden Age document events during this period with no signs of a global time skip. These societies had their own independent calendars, astronomical logs, and historical archives that align with Western records. Then there's the carbon dating problem. Radiocarbon analysis of artifacts from the Phantom period like the Oseberg Viking ship or the Book of Kells matches their placement in conventional timelines. Critics argue tree ring gaps could result from localized climate anomalies, not missing centuries. As for the calendar discrepancy, historians note that the Julian calendar's leap year system wasn't consistently applied, explaining the shorter drift Illig found. The hypothesis's real weakness, though, is Occam's razor. Inventing 300 years of history would require a conspiracy vaster than the events it supposedly erased. Yet the theory lingers because it taps into a deeper skepticism. How much of history is fact and how much is consensus? We rely on fragile chains of documentation, vulnerable to error, bias, or even deliberate myth-making. The phantom time hypothesis might be wrong, but its persistence reminds us that the past is always a story, one we reconstruct, not just receive. And sometimes the most compelling fictions reveal truths about how fragile our grip on reality really is. Do you vividly recall the Berenstain Bears books from childhood spelled with an E instead of the actual A? Or swear Nelson Mandela died in prison during the 1980s despite him passing in 2013? Welcome to the Mandela effect, a phenomenon where large groups share vivid but demonstrably false memories. This isn't just misremembering, it's collective false memory on a scale that sparked wild theories about reality itself. The term was coined by paranormal researcher Fiona Broome, who noticed countless people, herself included, remembered Mandela dying decades before his actual death. But the examples multiply. Monopoly's monocle-wearing mascot, he never had one. The fruit of the Loom Cornucopia logo, it doesn't exist. Or even Darth Vader's iconic line, "Luke, I am your father," was never spoken in The Empire Strikes Back. The real line, "No, I am your father." These discrepancies aren't minor typos. Thousands confidently recall details that vanish from historical records overnight. Some psychologists chalk this up to confabulation, our brains filling gaps with plausible fabrications. Memory isn't a video recording, it's reconstructive, stitching together fragments with biases and social influences. Once one person misremembers Berenstain, the error spreads like a cognitive virus, but others propose far stranger explanations. Could the Mandela effect hint at parallel realities bleeding into ours? Quantum decoherence, the same process that isolates parallel worlds in Everett's many-worlds interpretation, offers a tantalizing pseudo-explanation. If reality constantly branches, perhaps occasional crosstalk between timelines overwrites collective memory. Think of it like a corrupted hard drive where files from alternate versions of you bleed into this timeline's folders. The Berenstain universe and the Berenstein universe might have briefly merged, leaving some stranded with hybrid memories. Skeptics point out simpler causes: false branding rumors, the human brain's love for patterns, and "ein" ending feels more familiar than "ein," or even the fallibility of oral tradition. But the effect's persistence raises deeper questions about consensus reality. If our shared past can shift without a trace, how do we trust any memory or even history itself? The Mandela effect doesn't just challenge what we remember, it makes us wonder who or what is writing the script. What if life isn't just a passenger in the universe? What if it's the driver? This is the radical proposition of biocentrism, a theory that flips the traditional script of reality by placing biology at the center of cosmology. Spearheaded by scientist Robert Lanza, biocentrism argues that life and consciousness aren't accidental byproducts of physics. They're the very reason the universe exists at all. Imagine a painter who steps back to admire their canvas, only to realize the painting only exists because they're looking at it. In Lanza's view, reality works the same way. It doesn't solidify until a conscious observer interacts with it, weaving the fabric of existence from the threads of perception. Lanza's ideas spring from quantum mechanics' most baffling feature, the observer effect. In the double-slit experiment, particles behave as waves when unobserved, but collapse into definite positions the moment they're measured. Mainstream physics chalks this up to interactions with detectors, but Lanza goes further. What if it's not the detector causing the collapse, but the awareness of an observer? He points to delayed choice experiments, where decisions made in the present seem to retroactively alter a particle's past behavior. It's as if the universe waits for a mind to make up its mind, like a choose-your-own-adventure book where the story only unfolds when you turn the page. Critics dismiss this as quantum mysticism. Physicists like Sean Carroll argue that quantum systems can decohere into definite states without any conscious observer. A stray photon or dust particle can trigger the collapse just as well as a human brain. Philosophers add another layer. If consciousness creates reality, why does the universe appear so old and vast? A biocentric cosmos wouldn't need galaxies billions of light years away unless life somehow requires their existence. Lanza counters with the anthropic principle. The universe must be vast and ancient because otherwise we wouldn't be here to observe it. Yet biocentrism's most startling claim isn't about quantum mechanics, it's about time and space. Lanza argues these aren't fundamental realities but tools our minds use to organize experience. Think of a video game engine that only renders the part of the world the player is currently exploring. Similarly, our brains might construct time and space as a framework to navigate reality, not as aspects of reality itself. This echoes Kant's transcendental idealism, but with a biological twist. Space-time isn't just a mental filter. It's a byproduct of living systems interacting with the world. The theory's weakest spot, testability. Unlike traditional physics, which makes precise predictions about particle collisions or galactic motions, biocentrism struggles to offer falsifiable experiments. If consciousness shapes reality, how could we design a test that distinguishes this from ordinary quantum decoherence? Lanza points to studies showing that human intention might influence random number generators or plant growth, but these remain fringe claims lacking rigorous reproducibility. Biocentrism's real power lies in its audacity. By placing life at the center of cosmology, it forces us to reconsider our place in the universe. Are we passive specks in a vast, uncaring void or participants in a grand dance where observation and existence are inextricably linked? Whether Lanza's vision holds up to scrutiny or not, it reminds us of a profound truth. Reality, whatever it is, becomes meaningful only when there's someone there to experience it. And that might be the most biocentric fact of all. What if our entire universe isn't expanding into space, but falling deeper into an unfathomable abyss? This is the spine-tingling premise of black hole cosmology, a theory that suggests we might all be living inside the event horizon of a colossal black hole. At first glance, it sounds like science fiction, but the math holds a haunting allure. When you peer into the equations describing black holes and the Big Bang, they start to look eerily similar. both involve singularities, infinite densities, and the violent birth of spacetime itself. Could the Big Bang have been the moment a dying star collapsed into a black hole in some higher dimensional parent universe, birthing our cosmos in its crushing depths? Roger Penrose, the Nobel-winning physicist, took this idea even further with his conformal cyclic cosmology. Picture the universe not as a one-time explosion, but as an endless cycle of eons, each ending in a heat death so complete that all particles lose their mass, stretching spacetime into a featureless void. But here's the twist: that void becomes the seed for the next Big Bang. Penrose argues that the conformal boundaries between these eons, stripped of scale but preserving geometric relationships, could allow information to cross over. He even claims to have spotted faint imprints of previous universes in the cosmic microwave background, like ghostly fingerprints lingering in the static. Then there's the white hole speculation, a theoretical twin to the black hole, where matter and energy erupt outward instead of vanishing inward. If black holes are cosmic drains, white holes would be fountains spewing out newborn spacetime. Some theorists suggest our universe's Big Bang might have been the explosive rebirth of a white hole, recycling the remnants of a collapsed universe. The implications are staggering. Instead of a lonely, one-shot cosmos, we could be part of an infinite Russian nesting doll of realities, each born from the corpse of another. Critics pounce on the lack of direct evidence. How could we ever peek beyond our event horizon to see the parent universe? But supporters point to eerie symmetries. The observable universe's radius aligns suspiciously close to the Schwarzschild radius of a black hole with equivalent mass. Even the universe's accelerating expansion could mirror the tidal forces near a singularity. And if Hawking radiation causes black holes to evaporate over eons, might our own universe's fate be a slow fade into nothingness, or the prelude to another cycle? The theory's beauty lies in its economy. No need for multiverses or divine creators, just gravity's relentless logic playing out on cosmic scales, but it also forces a humbling thought. If we're inside a black hole, then every galaxy, every quasar, every flickering candle of life exists in the shadow of an unfathomable maw, a cosmic womb that could, at any moment, become our tomb. What if the Big Bang wasn't the beginning, but the aftermath? The ekpyrotic universe theory offers a jaw-dropping alternative where our cosmos wasn't born from a single explosive moment, but from the collision of two cosmic giants, vast, multidimensional membranes drifting through a higher dimensional space. Picture two sheets of paper floating parallel to each other in an empty room, silently inching closer until, boom, they slam together with enough force to ignite every star, planet, and galaxy in existence. This isn't just poetic imagery, it's the backbone of a model so precise it rewrites the origin story of everything. Unlike the classic Big Bang, which starts with a singularity of infinite density, the ekpyrotic scenario begins with two flat, infinite branes, short for membranes, existing in a higher dimensional bulk space. These aren't physical objects in the usual sense, but dynamical surfaces where particles and forces like gravity and electromagnetism are confined, like shadows dancing on the walls of a higher dimensional cave. According to string theorists Paul Steinhardt and Neil Turok, these branes could have been drifting apart for eons, stretching and cooling, until their mutual attraction pulls them back for a cataclysmic reunion. The energy of that collision wouldn't just create matter, it would stretch and flatten the branes so perfectly it explains why our universe looks so uniform on large scales. The elegance of this model lies in its solutions to cosmology's nagging puzzles. Take the horizon problem. Why does the cosmic microwave background look so eerily similar in opposite corners of the sky if there wasn't enough time for those regions to interact after the Big Bang? Inflation theory proposes a rapid expansion to smooth things out, but the ekpyrotic universe doesn't need it. The brane's pre-collision stretching achieves the same uniformity naturally, like rolling out dough until every wrinkle disappears. Even the universe's controversial flat geometry, where parallel lines never meet, falls neatly into place, a geometric inevitability of infinite brains flattening against each other. Visualizing this isn't easy, but animations help. Imagine a dark void where two glowing grids approach each other slowly. As they near contact, tiny ripples, quantum fluctuations from their previous cycles appear on their surfaces. These ripples don't vanish when the brains collide. They imprint onto the newborn universe as density variations, eventually becoming the seeds for galaxies. The collision itself isn't a chaotic explosion, but a controlled energy exchange event, more like a cosmic thunderclap than a traditional bang. Afterward, the brains rebound, drifting apart to begin the cycle anew. Critics highlight the challenges. Detecting higher dimensions or gravitational waves from brain collisions remains speculative, though some hope future telescopes could spot circular patterns in the cosmic microwave background, an echo of pre-Big Bang vibrations. Others argue the model's reliance on fine-tuned initial conditions just replaces one mystery with another, but the theory's beauty is its cyclical nature. Instead of a one-and-done universe destined for heat-death, the ekpyrotic model offers rebirth, with each collision resetting the cosmic clock. The implications are staggering. If true, our universe isn't a lonely accident but one note in an endless symphony of collisions, each birthing new physics, new constants, perhaps even new forms of life. It's a vision where beginnings and endings blur, and the biggest bang of all might just be a chapter in an infinite story. What if the future could reach back and reshape the past? This isn't just a sci-fi trope. It's a serious proposal in physics known as retrocausality, the idea that effects can precede their causes in a time-symmetric universe. At its core, this theory suggests that time isn't a one-way street but a looping, interactive dance where past and future constantly influence each other. The roots of this mind-bending concept trace back to the Wheeler-Feynman absorber theory, a radical reimagining of electromagnetism proposed in the 1940s. Feynman and Wheeler asked a simple but profound question: why does light radiate outward from a source, never inward? Their answer flipped classical physics on its head. They proposed that when an electron accelerates, it emits radiation both forward and backward in time. The backward wave would normally cancel itself out except when there's an absorber somewhere in the future ready to catch the radiation. In this model, the absorber's existence is what allows the initial emission to happen in the first place, like an echo from the future guiding the past. It's as if the universe is a perfectly tuned feedback loop where the future helps write its own history. Quantum mechanics takes this even further with experiments like the delayed choice quantum eraser. Imagine firing photons one by one at a screen through a barrier with two slits. If you don't measure which slit each photon passes through, they behave like waves, creating an interference pattern. But if you place detectors at the slits to observe the photons' paths, the interference vanishes. The photons act like particles. Now here's the twist. In the delayed choice version, you wait until after the photons have passed the slits, but before they hit the screen to decide whether or not to erase the which path information. Astonishingly, the photon's behavior changes retroactively, as if your future choice determines whether they acted as particles or waves in the past. This isn't just theoretical sleight of hand. In 2012, researchers at the Australian National University performed a version of this experiment using helium atoms scattered by laser beams. By randomly choosing to measure or erase the atoms' paths after they'd already moved through the apparatus, they found the atom's earlier behavior shifted to match the later decision. It's as if the universe refuses to commit to a single version of events until all possible observations are accounted for, even those made after the fact. Critics argue this doesn't truly imply backward causation, just that quantum systems remain in superposition until all relevant information is settled. But proponents of retrocausality see it differently. If the future can influence the past, even in limited quantum contexts, it challenges our deepest assumptions about time's arrow. Perhaps causality isn't a strict chain of cause and effect, but a web of interconnected events, where now is just a local illusion in a timeless whole. The implications ripple outward. If time is symmetric, free will takes on new dimensions. Our choices might not just shape the future, but retroactively refine the past. Cosmology, too, gets a twist. The universe's fine-tuning could be the result of future conditions, selecting the right initial parameters, like a sculptor chiseling away at time itself. Even entropy, the measure of disorder that gives time its apparent direction, might emerge from this two-way interplay. The time-symmetric universe doesn't just bend our perception of reality, it shatters the hourglass entirely, leaving us with a cosmos where past, present, and future exist in a delicate, dynamic balance. Whether this is the true nature of time or just a mathematical quirk, one thing's certain: the line between cause and effect has never looked so blurry. What if everything you see, the screen in front of you, your hands, even the stars, is nothing more than a user interface, a simplified dashboard hiding the incomprehensible chaos of true reality? This is the startling premise of Donald Hoffman's conscious realism, a theory that merges evolutionary biology with radical philosophy to suggest our senses don't show us the world as it is, but as we need to see it to survive. Picture your perception like a smartphone's home screen. The colorful icons for phone or camera aren't literal representations of the circuitry inside. They're symbols designed for quick, functional use. Hoffman argues our entire experience of reality works the same way. Evolution didn't shape us to perceive truth, it shaped us to perceive fitness, crafting a survival-oriented illusion that keeps us alive long enough to reproduce. Hoffman's evidence comes from evolutionary game theory. Imagine two ancestral creatures. One sees reality accurately, deciphering quantum fields and space-time curvature, while the other sees a simplified world of solid objects, clear boundaries, and cause and effect. Which survives? The second, every time. Processing the full complexity of reality would be like trying to navigate New York City by studying every atom in every street sign, overwhelming and useless. Instead, our brains filter the noise, presenting a cartoonish but functional map where fruits are red when ripe, snakes are dangerous when coiled, and cliffs are high enough to avoid. These aren't properties of the world itself, but symbols in a survival interface. The implications are staggering. If space, time, and physical objects are just evolutionary icons, what's the real operating system beneath? Hoffman proposes conscious agents, fundamental units of perception that interact to construct shared realities, like avatars in a multiplayer game agreeing on virtual physics. In this view, even the laws of nature might be local rules of engagement, not universal truths. Think of video games. Super Mario's gravity works differently than Call of Duty's, yet both feel consistent to players. Similarly, our universe's constants, the speed of light, Planck's length, could just be settings in a deeper simulation. Critics pounce on the theory's lack of empirical teeth. If reality is an illusion, how could we ever study what's behind the curtain? Hoffman counters with mathematical models showing how conscious agents, following simple rules, could generate the appearance of spacetime and objects without them being fundamentally real. It's like proving a chess game could emerge from players agreeing on moves, even if the board and pieces are imaginary. Even quantum mechanics gets a fresh spin. Wave function collapse might not be about particles choosing states, but about conscious agents updating their shared interface. The theory's real power lies in unifying hard problems, from quantum weirdness to the nature of consciousness under one framework. If perception is an interface, then the hard problem of why we have subjective experience at all becomes trivial. Consciousness isn't in the interface, it is the interface. And if spacetime isn't fundamental, it explains why quantum particles can seem entangled across distances they're not. in space to begin with, just rendered that way for our convenience. Yet the biggest question remains, why would evolution bother with this particular illusion? Why trees, stars, and not, say, floating hypercubes or pulsating fractals? Hoffman's answer is grimly practical. Those ancestors who saw useful fictions outbred those who saw useless truths. Reality, in this light, isn't a revelation, it's a negotiation, a collective hallucination so seamless we mistake it for the world itself. And if Hoffman's right, the greatest magic trick isn't pulling a rabbit from a hat, it's convincing us the hat was real to begin with. The Omniverse isn't just a playground for superheroes in Marvel Comics, it's one of the most staggering concepts in theoretical cosmology. A vast tapestry where every possible multiverse, every alternate reality, every variation of existence spins together in an unfathomable cosmic web. Think of it as the ultimate superset of reality, where even the wildest multiverse theories, branched timelines, bubble universes, simulated worlds are just single threads in an infinite dimensional loom. Physicist Max Tegmark's hierarchy of multiverses gives us a roadmap to this chaos, stacking realities like layers in a cosmic onion. Level 1. Parallel universes born from infinite space, where copies of you exist in distant, unreachable regions. Level 2. Bubble universes with different physical constants, forever inflating beyond our cosmic horizon. Level 3. The quantum many-worlds, where every decision spawns new branches. But Level 4, the Omniverse, is where Tegmark's math detonates all limits. Here, every mathematically coherent structure exists as a physical reality, from universes where time flows backward to ones where gravity repels and dreams take solid form. Marvel's version plays this for drama, alternate Spider-Men colliding, Thanos variants warring, but the real science is stranger. Imagine a library where every book isn't just a story, but a full universe with its own rules. Some volumes contain familiar physics, others read like LSD-fueled poetry, with laws so alien our brains can't pass them. The Omniverse doesn't care what's plausible or probable. If it can be described mathematically, it's out there, humming in the void. String theory hints at this with its 10 to the 500 possible vacuum states, each a potential universe with unique particle masses and forces. But the Omniverse goes further, housing not just string theory's options but all options. Universes made of pure sound, where information is currency, or where causality loops like a Möbius strip. Critics argue this is metaphysics disguised as physics. How could we ever test a theory that includes literally everything? Tegmark's rebuttal is sly. The fact that we exist in a universe stable enough for life is the evidence. In an Omniverse, of course, we'd find ourselves in a self-consistent corner, just as a fish born in a pond assumes water is universal, the real shocker. If the Omniverse is real, then every fictional world from Middle-earth to the Star Wars galaxy exists somewhere in the stack, not as metaphors but as physical realities vibrating in their own mathematical frequencies. Yet the most haunting question isn't about what's out there, but what it means for here. If every possible version of you exists, the one who became a billionaire, the one who never woke up today, does choice lose meaning? Not necessarily. Your decisions still shape which thread of the Omniverse this version of you experiences. It's less about fate and more about navigation. In an infinite ocean, the wind you catch still determines your sail. The Omniverse doesn't diminish us, it magnifies every moment, casting our lives as ripples in a sea without shores. Whether it's science or philosophy, one thing's certain: reality, in its fullest sense, is bigger than our wildest dreams and our nightmares too. What if the entire universe is nothing more than an elaborate cosmic free lunch? The zero-energy universe theory proposes just that. A mind-bending calculation where all the positive energy in stars, galaxies, and even your morning coffee is perfectly balanced by negative gravitational energy, leaving the sum total of existence at exactly zero. This isn't just philosophical wordplay, it's hard mathematics rooted in general relativity. When you calculate the universe's total mass energy, thanks to Einstein's famous E=mc², and pit it against the negative potential energy of gravity stretching across cosmic distances, the two figures cancel out with eerie precision. It's like depositing $1 million in one bank account while owing $1 million elsewhere. Your net worth hasn't actually changed. This balancing act traces back to quantum mechanics' most unpredictable players, virtual particles. In the vacuum of space, particle-antiparticle pairs constantly blink into existence, borrowing energy from nothingness before annihilating and paying it back almost instantly. These quantum fluctuations aren't breaking any rules. Heisenberg's uncertainty principle allows such brief energy loans, provided they're settled quickly. Now scale this up cosmically. If a universe could pop into being the same way, with positive matter energy and negative gravitational energy balancing to zero, it wouldn't violate energy conservation any more than those fleeting particle pairs. The universe wouldn't need a creator or external energy source. It could literally be the ultimate something-from-nothing trick. Alan Gough's inflationary theory adds weight to this idea. During the Big Bang's first fractions of a second, the universe expanded exponentially, with gravity's negative energy perfectly offsetting the positive energy of newly created matter. Picture a balloon inflating. As the rubber stretches positive energy, the tension within it builds negative energy, keeping the system in equilibrium. The vacuum energy driving inflation wasn't used up, it was temporarily borrowed, then repaid as matter and gravity cancelled each other out. But where did the original quantum fluctuation come from? Some theorists invoke the no-boundary proposal. Stephen Hawking and James Hartle's suggestion that time at the quantum level behaves like space, creating a closed surface without a singular beginning point. In this model, asking what happened before the Big Bang becomes as meaningless as asking what's north of the North Pole. Others see the zero-energy universe as evidence for spontaneous self-creation, where the utter absence of prior conditions is precisely what allows existence to emerge. After all, if nothing is truly neutral rather than empty, then nothing might be the most unstable state of all, a powder keg of potential universes waiting to ignite. The zero-energy hypothesis doesn't just reshape our origin story, it redefines our cosmic identity. If the books truly balance at zero, then every galaxy, every atom, every thought is fundamentally free. An intricate dance of opposing energies that, in the grand ledger, amount to nothing at all. Yet here we are, exploring the very reality that supposedly doesn't exist. That paradox might be the theory's most profound gift, the realization that nothingness, properly understood, contains everything. What if the eerie fine-tuning of our universe, the impossibly precise constants that allow galaxies, life, and even your thoughts to exist, isn't a cosmic fluke or divine handiwork, but the statistical inevitability of infinite holographic projections? This is the spine-tingling promise of the holographic anthropic multiverse, a theory that weaves together two of physics' most radical ideas into a single tapestry. Start with the holographic principle, the notion that our three-dimensional reality is a projection from a two-dimensional surface at the universe's edge, like a movie playing on the screen of a black hole's event horizon. Now layer on the anthropic principle the observation that we can only exist in a universe capable of supporting life, no matter how improbable its parameters. Combine them, and you get a vision of existence where every possible variation of physical laws flickers into being across countless holographic membranes, with conscious observers like us naturally finding ourselves in the rare slices where conditions align just right. Think of it like a cosmic casino with infinite slot machines. Each machine represents a holographic universe with randomly dialed constants: the strength of gravity, the mass of electrons, the dark energy density. Most combinations spit out cosmic gibberish, universes that collapse instantly or where atoms never form or time shatters into fragments, but in a few machines, by sheer probability, the reals land on life-friendly numbers. We're not special for winning, we're just the players who could win, blinking into existence in the holograms where the math allows it. This isn't magic, it's combinatorics on a multiversal scale, where even the most improbable outcomes become certain given enough rolls of the dice. The holographic angle adds a surreal twist. If our universe's physics are encoded on a distant 2D boundary, then the fine-tuning might not happen here at all, but in the deeper mathematical substrate where those boundary conditions are set. Imagine a programmer writing code for a video game. They don't tweak each pixel individually. They adjust the underlying algorithms that generate the world. Similarly, the holographic multiverse could be running endless variations of its source code, with our perceived reality just one rendering of a deeper informational landscape. This explains why the universe seems so improbably balanced. We're literally inside the projection that passed QA testing. Critics argue this is circular reasoning. Of course, we observe a universe that supports observers. But proponents fire back with quantum cosmology's latest tools. In some models of eternal inflation, bubble universes with different laws constantly nucleate and collide, leaving imprints in each other's cosmic microwave backgrounds like bruises from a multidimensional bumper car ride. If these bubbles are holographic, their physics determined by boundary conditions, then the multiverse isn't just vast, but layered, with each bubble's 3D reality unfolding from a 2D blueprint we can't yet decode. The most unsettling implication: if this is true, our entire cosmos might be the equivalent of a QR code, a compact, two-dimensional data structure that only appears vast and three-dimensional when scanned by the right kind of observer. The fine-tuning isn't a puzzle to solve, but a user agreement we implicitly accepted by waking up in this particular projection. And somewhere in the infinite library of alternate holograms, there are versions of reality where the constants failed, and no one ever got the chance to wonder why. What if the atoms in your body, the stars in the sky, even the thoughts in your mind aren't made of matter or energy, but of information? This is the radical proposition of physicist Melvin Vopson, who argues that reality at its most fundamental level isn't built from particles or waves, but from bits, the same ones and zeros that power your smartphone. His theory of mass-energy information equivalence takes Einstein's iconic E equals mc squared and adds a daring third term, information. In this equation, information isn't just a description of reality. It's the substance reality is made of, with measurable mass and energy, just like protons or photons. Vopson's math suggests that every bit of information, whether stored in DNA, etched onto a hard drive, or encoded in the spin of an electron, has a tiny but calculable mass. How tiny? About a millionth of a trillionth of a trillionth of a gram per bit. That might seem negligible, but scale it up to the estimated 10 to the 93 bits of information in the observable universe, and suddenly information's gravitational footprint becomes impossible to ignore. This leads to a staggering implication. Deleting data from a hard drive doesn't just erase ones and zeros, it might literally make the drive lighter, as if information itself were a physical ingredient in the cosmic recipe. The theory's most tantalizing evidence comes from antimatter annihilation, the process where particles and their antiparticle counterparts collide, converting their mass into pure energy. Vopson argues that when matter and antimatter annihilate, they don't just release energy, they erase information. The particles' identities, positions, and histories vanish from the universe's ledger, and Vopson's equations predict this information loss should produce a detectable energy signature matching his mass-energy information equivalence. Future experiments aiming to measure the infrared glow from antimatter reactions could put this to the test, potentially offering the first proof that information has tangible weight. Critics pounce on the theory's speculative leaps. thermodynamics traditionally treats information as abstract, not a physical substance. You can't weigh a Wikipedia page on a scale. Skeptics like physicist Sabine Hossenfelder argue that Vopson conflates mathematical models with physical reality, like mistaking a map for the territory. Even if information has energy, as Landauer's principle shows when erasing computational bits, that doesn't necessarily mean it's a fundamental building block. Others question how Vopson's theory accounts for quantum information, which can exist in superpositions or become entangled across vast distances, properties that don't neatly fit classical bit-based frameworks. Yet the theory gains eerie traction when applied to black holes. Hawking radiation implies that information swallowed by a black hole isn't truly destroyed, just scrambled and eventually leaked back out. If information carries mass, this could explain why black holes have gravity. They're not just trapping matter, but the information that matter encodes. Even the holographic principle finds a new angle here. If our 3D universe is a projection from a 2D surface, perhaps the pixels of that surface are literal bits, with space-time itself emerging from their computations. Vopson's boldest extension, the second law of infodynamics, a proposed sibling to thermodynamics entropy that claims information in isolated systems tends toward equilibrium, just like temperature. He suggests this could explain everything from evolutionary patterns to the symmetries of particle physics, as if the universe were constantly optimizing its data storage. Imagine DNA mutations not as random errors, but as the genetic code naturally compressing or error-correcting itself to meet this law's demands. Whether Vopson's vision holds up or not, it forces us to confront a profound shift in perspective. For centuries, science has treated information as a passenger riding atop physical processes, a book about atoms, not the atoms themselves. But if information is truly fundamental, then reality might be less like a machine and more like a cosmic Wikipedia, endlessly editing itself into existence. The next time you delete a file or forget a memory, you might be participating in physics' deepest mystery, not just how matter behaves, but what it is. What if we're all higher dimensional beings trapped in a lower dimensional prison, unaware of our own vastness? This is the startling premise of dimensional consciousness theory, a fusion of mystical philosophy and cutting-edge physics that suggests our perception of reality is radically limited by the dimensions we inhabit. Picture an ant walking along a telephone wire. From its flat, narrow perspective, the wire is a one-dimensional line. Only when we, as three-dimensional observers, look down can we see the wire's full shape, its twists, its connection to poles, the vast landscape around it. Now imagine that same ant is us and the wire is our entire universe. What if we're just as blind to the full scope of existence? Russian mystic P. D. Ouspensky, writing in the early 20th century, proposed this idea decades before modern physics caught up. He argued that human consciousness is asleep in 3 dimensions, perceiving only shadows of a richer, multidimensional reality. To Ouspensky, higher dimensions weren't just mathematical abstractions, they were planes of awareness. A 4th-dimensional being wouldn't just see through walls, it would perceive time as a landscape, witnessing past, present, and future simultaneously like pages in a book. Our linear experience of moments one after another might be an illusion born of dimensional limitation, like a stick figure unable to comprehend depth. Fast forward to string theory, where extra dimensions aren't mystical but mathematical necessities. To make their equations work, physicists posit 6 or 7 compactified dimensions curled up into structures called Calabi-Yau manifolds, tinier than an atom. These aren't science fiction, they're complex geometric shapes that could dictate everything from particle masses to the strength of gravity. But here's where consciousness re-enters. What if these hidden dimensions aren't just physical but perceptual? Imagine a Calabi-Yau shape not as a tiny knot in space but as a folding of awareness itself, a higher dimensional lens that, if we could uncurl it, would reveal layers of reality currently invisible to us. This intersection of mysticism and physics isn't accidental. Quantum entanglement, where particles instantly influence each other across vast distances, makes perfect sense in higher dimensions. What looks like spooky action at a distance in 3D could be mundane proximity in 4D. Even déjà vu might get a scientific gloss. If time is a higher dimensional structure, those eerie feelings of repetition could be fleeting glimpses of parallel timelines brushing against ours. The theory's most profound implication isn't about physics but identity. If higher dimensions alter perception, then expanding consciousness might mean literally seeing more dimensions. Meditation, psychedelics, or near-death experiences that describe breaking through to vast, interconnected realities could be glimpses beyond the 3D veil. It's a vision where spirituality and science meet not as rivals but as different paths up the same mountain. Critics dismiss this as speculative, arguing that extra dimensions in string theory lack empirical proof, let alone ties to consciousness. But pioneers like neuroscientist Carl Pribram found eerie parallels between holographic brain function and higher dimensional math, suggesting perception might already be processing hidden dimensions we can't consciously access. Whether metaphor or physics, dimensional consciousness theory leaves one haunting question. What if the universe isn't stranger than we imagine, but stranger than we can imagine, simply because we're stuck in dimensional handcuffs, blind to the full spectrum of our own existence? How does a world of concrete objects and definite facts emerge from the fuzzy quantum realm, where particles exist in ghostly superpositions until observed? Quantum Darwinism offers a breathtaking answer, one where reality isn't imposed by conscious observers, but forged through a relentless process of natural selection at the quantum level. At the heart of this theory lies Wojciech's revolutionary insight. What we call objective reality isn't fundamental. It's the winner of an invisible competition where only the sturdiest quantum states survive the chaotic onslaught of their environment. Picture a lone electron in a lab, its spin pointing both up and down simultaneously, a textbook quantum superposition. Now imagine this electron gets jostled by passing air molecules, struck by stray photons, or nudged by vibrations in the lab bench. These tiny interactions aren't random noise, they're the universe's ultimate fact-checkers. Each collision tests the electron state, but not all outcomes are created equal. Some quantum states, called pointer states, are robust, like a tree bending in the wind but never breaking. Others are fragile, collapsing instantly under environmental pressure. Over countless interactions, only these resilient pointer states endure, while their delicate counterparts vanish like mist in sunlight. Jack realized this process mirrors biological evolution. Just as natural selection favors traits that enhance survival, quantum decoherence favors states that withstand environmental scrutiny. The catch: these surviving states don't just passively endure, they replicate their information outward, imprinting copies onto their surroundings like graffiti sprayed across the cosmos. When you measure an electron's spin, you're not causing its wave function to collapse, you're catching one of the countless redundant imprints it's already left on the environment. Reality becomes objective, not because it's absolute, but because its signature is scribbled everywhere, available for any observer to read. This explains why we all agree on the color of the sky or the position of the moon. It's not that these things exist independently of us, it's that their quantum states have been so thoroughly broadcast through decoherence that every conscious being accesses the same environmental records. Think of it like a viral tweet. The reason millions see the same message isn't that one person's phone holds the true version, but because the information has been copied so widely it becomes impossible to ignore. Critics argue this merely shifts the mystery from observers to environments. Why should certain states be more stable? The answer lies in einselection, short for environment-induced superselection. Some quantum properties, like position or momentum, naturally resist decoherence because they're tied to conserved quantities like energy. An electron's location might leave robust imprints on surrounding particles, while its phase relationship with distant electrons, a fragile quantum whisper, gets obliterated by the slightest disturbance. The universe, it seems, has built-in preferences for which features get etched into reality's ledger. The implications ripple outward. Quantum Darwinism suggests the classic divide between quantum weirdness and classical certainty is an illusion. There's no magical threshold where superposition ends and objectivity begins, just an endless fractal cascade of information copying, with more redundant imprints creating the appearance of solidity. Even time's arrow might emerge from this process as decoherence irreversibly proliferates certain states while erasing others. Most hauntingly, the theory redefines what observation means. You're not a privileged spectator collapsing reality into being. You're a latecomer browsing environmental records left by countless prior interactions. The moon exists when nobody looks, not because it's fundamentally classical, but because its pointer states have been broadcast so thoroughly that their absence would require rewinding the universe itself. Quantum Darwinism doesn't just explain how reality emerges. It reveals how deeply we're entangled in the process, not as kings of creation, but as participants in an ancient, unthinking game of information survival. Most Western thought begins with division: mind versus body, self versus world, observer versus observed. But what if these splits are illusions, the mental equivalent of a mirage flickering over a deeper, seamless reality? This is the heart of Advaita Vedanta, India's ancient non-dual philosophy, which insists that consciousness isn't something we have but what we fundamentally are, an infinite, undivided awareness temporarily wearing the costume of individuality. The 20th century sage Ramana Maharshi put it bluntly: "The world is unreal, Brahman alone is real. Brahman is the world." At first glance, this sounds like solipsism or idealism, but Vedanta's revelation is subtler. It's not that the world doesn't exist, it's that it never existed separately from the consciousness perceiving it, like waves never existing apart from the ocean. Modern neuroscience stumbles toward this realization in its study of the selfing brain. Default mode network activity, the neural circuitry responsible for autobiographical narrative, quietly constructs our sense of being a separate I navigating an external world. When this network deactivates during deep meditation or psychedelic experiences, subjects report ego dissolution, a melting of boundaries where observer and observed merge into a unified field. Stanford researchers studying long-term meditators found their brains exhibit functional dedifferentiation, where sensory and self-referential regions sync into harmonious patterns, as if the brain is unlearning the habit of division. It's as if Advaita's ancient claim that separation is a cognitive habit, not an ultimate truth, is being echoed in the language of fMRI scans. The contrast with Western dualism couldn't be sharper. Descartes' "I think, therefore I am" enshrined the mind-body split, while Newtonian physics framed reality as a clockwork mechanism ticking independently of observers. Even quantum mechanics, which shattered this detached worldview, gets reinterpreted through dualist lenses. We speak of particles collapsing when measured, preserving the myth of a separate experimenter. Vedanta dismantles this scaffolding entirely. In its view, the universe isn't a machine to be dissected but a living process of consciousness exploring itself through infinite forms. When Maharshi was asked how to treat others, he replied, "There are no others." Critics dismiss this as mystical hand-waving, but clues emerge from unexpected places. Integrated information theory, a leading model of consciousness, posits that subjective experience arises from irreducible causal interactions within a system, a mathematical echo of Vedanta's neti-neti, not this, not that, where reality can't be reduced to parts. Even holographic principles resonate here. If the universe is a projection from a boundary, then the apparent divisions within it might be as illusory as the pixels on a screen pretending to be separate from the image. Yet non-duality's greatest challenge isn't intellectual but experiential. How do you live as undivided awareness when your brain keeps generating the fiction of separation? Vedanta's answer is deceptively simple self-inquiry by relentlessly asking, "Who am I?" Not to find an answer but to dissolve the questioner, the mind's grip loosens. Neuroscientist Richard Davidson found that advanced meditators can voluntarily dampen their default mode networks, as if practicing ego death like a muscle memory. The goal isn't to escape the world but to see through its apparent duality, like waking from a dream while still dreaming. The implications ripple far beyond metaphysics. If non-duality is real, then ecological crisis isn't just a technical failure but a perceptual one, the delusion that we can harm nature without harming ourselves. Social divisions dissolve under the same lens. Racism, sexism, and nationalism all rely on the primal error of separation. Advaita doesn't offer easy solutions, but it reframes every problem. When the boundary between self and other vanishes, compassion isn't altruism, it's common sense. Perhaps the most startling convergence lies in quantum vacuum fluctuations. The void of space isn't empty but seething with potential particles flickering in and out of existence, a modern parallel to Vedanta's Brahman, the ground of being that's neither existence nor non-existence. In this light, non-duality isn't Eastern mysticism but a framework waiting for science to catch up, where consciousness isn't a latecomer to the cosmos but its primordial fabric. The final irony: the harder we look for ultimate divisions, the more the universe whispers back, "You've been here all along." From simulated worlds to cosmic holograms, from lonely solipsistic minds to branching multiverses, we've traveled through a labyrinth of theories that twist reality like a funhouse mirror. Each one peels back another layer of what we thought we knew, challenging the bedrock of existence itself. Think about the simulation hypothesis, the unsettling possibility that every star, every atom, even your memories might be lines of code in some unfathomable computer. Or the holographic principle, suggesting the three-dimensional universe around us is just a projection from a distant two-dimensional surface, like a shadow cast by a fire we can't see. And then there's solipsism, the ghost in the machine of philosophy. What if you're the only mind that truly exists and everything else is an elaborate hallucination? These aren't just thought experiments, they're seismic shifts in perspective, forcing us to confront the limits of human understanding. Reality, or whatever we're calling it, isn't a fixed stage. It's a negotiation, a dynamic dance between observation, mathematics, and the sheer, stubborn strangeness of the cosmos. Why does this matter? Because every time we question the nature of existence, we're not just exploring the universe, we're exploring ourselves. The act of wondering whether we're brains in vats or players in a multiversal game isn't just about physics or philosophy. It's about humility. It reminds us that our grasp on truth is fragile, provisional, and infinitely expandable. So here's the real question. Does it unsettle you to imagine you're living in a hologram, or does it thrill you to think your consciousness might be woven into the fabric of space-time itself? Maybe you're convinced we're all Boltzmann brains, flickering into existence for just a nanosecond with false memories of a life that never was. Or perhaps you're betting on the Omniverse, where every possible version of you is out there, living every possible life. Whatever your gut reaction, that's where the magic happens. The theories might bend your mind, but the conversation, that's where we push the boundaries together. Drop your wildest thoughts below. Which reality terrifies or electrifies you the most? The answers might just shape the next great theory or reveal something unexpected about the world.